All right, let's jump right into one of the most conceptual and high-scoring topics for JEE Mains, the dual nature of matter and radiation. In just the next few minutes, we're going to break down every key formula and graph you absolutely need to know to ace this chapter.
So, for years and years, scientists were totally stumped. Is light a wave or is it a particle? It was a huge debate. See, some experiments, like interference and diffraction, screamed, it's a wave. But then, other results came along that wave theory just couldn't explain, not at all. Those experiments only made sense if light was actually a tiny little particle.
So what was the answer? Well, it turns out it's both. How crazy is that? Light has this dual nature. Think of it like a master actor who can play two totally different roles. Depending on the situation, the experiment you're running, you'll see one of those roles. But you can never catch it playing both at the exact same time.
Okay, so let's zoom in on light's particle side. We're going to talk about the one phenomenon that completely broke wave theory. I'm talking about the photoelectric effect.
So to crack this puzzle, Einstein came up with a brilliant idea. He suggested that light doesn't travel as a continuous wave, but in these little, discrete packets of energy. He called them photons. And the energy of just one photon? Well, it's given by the famous equation E equals h nu, where h is Planck's constant and nu is just the frequency of the light.
Okay, but here's where it gets really cool. What happens when these photons actually hit a metal surface? Well, if a photon comes in with enough energy, it's like a tiny, superpowered billiard ball. It smacks into an electron and literally knocks it right out of the metal. That process of kicking electrons out with light is the photoelectric effect.
But hold on, it's not like any photon can do this. See, every metal has a certain grip on its electrons. There's a minimum amount of energy you need to supply just to break one free. We call this the work function. You can think of it as the electron's exit fee, the price it has to pay just to get out the door. And since we know a photon's energy is all about its frequency, right? That minimum energy, the work function, directly corresponds to a minimum frequency of light. This is super important. It's called the threshold frequency. If your light's frequency is below this threshold, nothing happens. I mean nothing. You can make the light incredibly break and still not a single electron will pop out.
So here's the bottom line. The photon's energy has to be at least equal to the work function or it's a no-go. The analogy is perfect. Think about buying a biscuit that costs 5 rupees. If you walk in with only 4 rupees, you're getting nothing, right? You need at least 5. It's the same deal for the electron. Less energy than the exit fee, and it's staying right where it is.
All right, now let's get to the main event, Einstein's winning equation. This is the simple yet ridiculously powerful formula he came up with to explain everything we've just talked about. And yeah, this is what won him the Nobel Prize.
And the equation itself, it's just so elegant. H nu equals phi plus Ke max. So the total energy that the photon brings in, H nu, gets split. Part of it is used to pay that exit fee. That's the work function, phi. And whatever is left over, that becomes the kinetic energy of the electron, making it move. It's just a perfect, simple statement of energy conservation.
Think of it like a simple budget. The photon comes in with a certain amount of energy. A fixed cost, the work function, has to be paid first. And the rest of the energy? That's the spending money that goes directly into making the electron move faster, giving it its kinetic energy.
Okay, theory's down. Now let's talk about something JEE absolutely loves, graphs. We're going to see how this equation looks visually, and trust me, you need to know these graphs inside and out for the exam.
First question for you. How does the kinetic energy of these photoelectrons change if we start playing with the frequency of the light? Changing its color.
Well, if you plot a graph of kinetic energy versus frequency, it tells you everything. Look here, the line doesn't start at 0. It starts at the threshold frequency. Before that point, nothing. But once you cross that threshold, the kinetic energy shoots up in a perfect straight line. And the best part? The slope of that line is none other than Planck's constant, h. It's all connected.
Okay, next graph. What happens if we keep the frequency the same, but we make the light brighter? In other words, we're cranking up the intensity. What does that do to the number of electrons flowing, the photoelectric current?
This one's actually pretty intuitive. More intensity simply means more photons are bombarding the metal every single second. More photons hitting means more electrons getting knocked out. And more electrons flowing means, you guessed it, a higher current.
It's a straight line relationship, right through the origin. Simple as that.
Now, this is a really clever concept. What if we wanted to measure the kinetic energy of the fastest electrons? How could we do that? Well, we can actually apply a reverse voltage, a negative voltage, to push back against them and try to stop them from reaching the other side.
And that exact minimum negative voltage you need to apply to bring the current to a dead stop, to stop even the most energetic electrons, that's what we call the stopping potential, or V0. It's awesome because it gives us a direct way to measure the maximum kinetic energy. KE max is just E times V0.
Okay, so just when everyone in the physics world thought, phew, we finally figured out light is weird, this guy Louis de Broglie comes along, and he asks a question so bold it turned everything on its head, all over again.
De Broglie's logic was just beautiful. He basically said, hey, nature loves symmetry, right? So if waves, like light, can act like particles, then why can't particles, like electrons, act like waves?
And it turns out he was totally right. He proposed that every single moving particle, from an electron to a cricket ball, has a wave associated with it. Its wavelength, which we call lambda, is just Planck's constant h divided by its momentum, p, which is just mass times velocity.
All right, time to wrap up. Let's do a quick recap with the ultimate formula box for this chapter. Seriously, screenshot this if you have to. These 5 equations are your lifeline. If you know these inside and out, you're going to be in great shape for any problem GE throws your way.
And that's it, your super fast revision of the dual nature of matter and radiation. But before you click away, here's a little something to think about. If every moving object has a wavelength, including you, why don't you see yourself diffracting or making wave patterns when you walk through a doorway? The clue is right there in de Broglie's equation. Give it some thought, and we'll catch you in the next one.